Hi all, it's Alan here and I'm back in my electronics cave again. Now, I've answered a lot of questions and debunked a lot of myths about clock timing in digital to analog converters, but I thought I'd do a long format video to explain a little bit more about what's actually going on, because there is an awful lot of rubbish spoken about how critical clocks are. Reclocking USB or Ethernet, for example, is widely done, but actually achieves very little. But I've also heard from some places that clock timing is irrelevant, which is also wrong. So let's take a look at this DAC. This particular one is a model by Arel, and I'll explain a little bit about what's going on and where clocking is important and where it's not. So first thing is, in terms of the design of this DAC, there are essentially three chips that are doing something really important in this DAC, and you can just about see them behind the pile of oscilloscope leads there. The first chip, which is this one here, is basically just an input chip. It just takes the input from the source, whether it's a CD player or a streamer in my case, and converts that into a usable bit stream that the CD player can then, that the D2A converter can then actually use. The second one, which is this little 16-pin one here, although it looks small, this one's actually doing a lot of work. This one is actually a miniature digital signal processor, which is doing 8 times oversampling. So it's taking that input signal and basically oversampling it 8 times and producing a signal of much higher bit resolution at much higher speeds to make the job much easier for the digital to analog converter. And that's what the third chip is. It's the actual digital to analog converter. In this case, it's an R2R DAC designed by Analog Devices, and a reasonably good one at that. So let me show you some traces so we can see a little bit of what's actually going on in the DAC. So this is actually some live traces of Björk playing at the moment in my CD player. And actually, if you take a look at these signals, there's basically 3 signals that are going into that final DAC chip. The top one is a clock signal that is clocking in the middle one, and the middle one is actually the audio data. So that data that's jumping around all over the place, that's because it's music, that's music data. Now, the top and the middle signals, actually timing of those isn't particularly critical, it's just about getting that data into the D2A converter. However, this is where things change. The signal at the bottom here is actually reasonably important. This is the latch input, and what actually happens here is every time there's a falling edge on this signal, it takes all of this data that's previously been clocked into the DAC and clocks it through onto the analog output. So the exact timing of that clock there, of when that's actually clocked through onto the analog output, that is important. And you can see it occurs once every audio sample size. So actually, that's reasonably critical. But what about it is actually important? So, the first thing you might think of is let's think about frequency. Is the exact frequency of that important? So let's think about that. The clock that actually drives all of this is actually running at, if this was a 44.1 kHz signal, it would actually be running at 16.9344 megahertz. And what would happen if that clock was running a bit slower, say for example 16.935 megahertz? Well, you do the maths and that would work out as an area of about 35 parts per million, which is quite a lot by modern electronic standards. But that would just make your music play slightly faster. And it's pretty insignificant actually. If you think about this in a typical 4-minute track, it would finish 0.008 seconds too soon. And I challenge anybody to hear that. It wouldn't introduce any distortion at all, just ever so slightly move the frequencies up a minuscule bit and make it run a minuscule bit faster. But if this particular clock edge, if this particular signal were to happen, say this one here, for example, this falling edge, if this was to happen 1 nanosecond sooner than it's supposed to, what would actually happen there is because that's clocking an individual sample into the analog stage, that would actually make the resulting analog output slope steeper or less steep than it should be. And most importantly, differently steep to the previous one. And that introduces distortion. And that we can very definitely hear. If one edge is too early and the next is too late and the timing moves around randomly, this is called phase jitter, and that's what we want to get rid of. Phase jitter on this one clock, and that's the only one that's really important in the entire system. So let's take a look back at this Arel DAC again then, and basically have a think about what clocks are actually going on in this circuit. And actually, this original design actually comes with 2 clock crystals. You can just about see one here in the middle of this design here. That's one there. Actually, that one's just used during startup. It basically, before there's any music going into this thing, it still needs a clock signal in order to basically get all of its digital signal processors running and make everything work. So that one's fine. That's not doing anything particularly critical. There's actually a second clock here, which is mounted on this board, and in this case, this is a fancy clock. It's running at 25 megahertz. And the 25 megahertz, that clock actually, you can just about see it's the pink wire, and that feeds into the digital signal processor in the middle. Now, actually, that's also not particularly critical. It's running at 25 megahertz, but So what? It's just basically doing the digital signal processing. It's just the clock to provide the high-speed maths. The critical timing doesn't actually come from either of these. It actually comes from a phase-locked loop, which is in that first Yamaha chip, and it's attempting to lock onto the input signal. So if we look at this example here, you can see that that signal there is actually running at 384 kilohertz, and that's no coincidence. My source at the moment is actually a 48 kilohertz source, and 384 kilohertz is an exact multiple of that. It's 8 times that frequency. Remember I said earlier that there's an 8 times oversampling chip in there. So that is the important frequency, that's the important one. And that's not an even multiple of either 20 megahertz or 25 megahertz. So in fact, in this case, that clock is coming from, it is being reverse engineered effectively from the digital signals that are coming into the DAC. And there are problems with this. The clock is trying to lock onto a frequency from the data. And we know that the data is using, well, that's using a phase-locked loop. And here, for example, I've got a cheap Chinese USB to SPDIF converter that's basically feeding an optical input into the back of this particular DAC. And actually, that means that it's a really, really poor clock signal. I mean, you've seen here the data. Actually, the data is a bunch of ones and zeros in no particularly stable order. And trying to reconstitute a clock signal from that is really quite challenging. So it's a bunch of ones, it's a bunch of zeros in varying quantities dependent on the audio that's playing at the time. Plus it may be coming from an optical input, in my case, which it is, where jitter is really bad. The latency, in fact, when a clock goes high, for example, the LED is turning on, is not the same as when it switches off. Even worse than that, the latency can be temperature and capacitance dependent. So if you've got a bunch of ones in a row, the switch on latency tends to be shorter, and a bunch of zeros in a row, vice versa. Even expensive converters, well, an awful lot better than this one, actually are inherently flawed. So the timing isn't great. So the question is, how can we do better? The problem, this would actually be easy if you just put a clock in the DAC, however, in order to generate that really accurate timing that we need. However, the reality is that the problem is that the clock also needs to be synchronized with the transport, or my streamer in this case. Otherwise, the DAC transport or transport may run out of data, causing a horrible glitch, or even worse, the data gets corrupted due to it being clocked at the wrong time. And we've already established that trying to create a 16.9344 megahertz low jitter clock from a mess of data is a problem. So how can we fix this? Well, I use a technique here called clock locking. Clock locking is an interesting technique. What we do is we create a clock in the DAC, and that's what this extra board is doing here. There are 2 crystals in here, in fact, X1 and X2. And what we've done here is we've chosen crystals that are very specifically chosen to have extremely low phase jitter. Note, these aren't temperature controlled oscillators or anything. They're actually designed to be highly accurate, which isn't what we care about. We care about jitter, and the temperature doesn't really impact this. So in this case, these crystals have been picked to have jitter of around 1 picosecond. In my own DAC designs, for example, over there, I'm actually using ones with considerably lower jitter still. They're using 50 femtosecond jitter crystals, or 0.05 picosecond jitter. And that clock data we actually feed via these orange and yellow wires directly into the DAC source itself. So the DAC, but there's no interposing cabling, no fibre optics, no phase-lock loop to mess it all up, none of those stuff. I also, however, feed it out to the transport via this cable here. And in this case, this could be a CD player, but in this case I'm using my own design of USB to SPDIF interface, which accepts this clock input as the master clock input to the USB chip. Switch on the clock lock, switch over to the other input, push play on my source, which in this case is my laptop, turn the volume back up, and you'll see there's a blue LED on the front of my USB input converter. That blue LED tells me that this is clock locked and that this USB converter is actually getting its clock from inside the DAC. So the benefit here, I get the really accurate clock, the really low jitter clock, right where I need it, right in the DAC, and it feeds pretty much directly into the analog to digital converter. The timing of the rest of the signals, all of these BNC connections, etc., is really not critical now, because the important clock is when we clock that final output data back out to the analog output. So the rest of it is just about getting data where it needs to be. The interface, the optics, even oversampling filters are provided with clock synced to this master clock, which basically the jitter and timing is relatively unimportant for those, but that critical timing in that final digital to analog converter stage is now great. I can even use optical connections from these. I said they're terrible from a timing perspective or from a jitter perspective, but it doesn't really matter here, because the important clock timing is all internal to the DAC. It's only going a couple of inches. They are, however, great at isolating electrical noise, so none of that horrible interference from an Ethernet connection in my PC, etc., would make it through to the DAC. But in this case, I've got a isolation, optical and magnetic isolation, actually in my USB interface, so it's not critical here. But if you're not using my USB interface, using optical converters and this kind of clock locking solution could be a really good way of stopping noise getting into your system. So I've got exactly what I want. I've got an almost perfect clock going in, it's synchronized to my transport, and it sounds absolutely stunning. So are there other ways of achieving this same kind of thing? Well, in short, yes, there are. Some DACs, for example, include a small amount of memory in the input to buffer the incoming data, allowing them to run off their internal clocks, even if they aren't perfectly synced. But in my opinion, the version I've done here is by far the best and simplest method of getting a really great sounding DAC. Now, different types of DACs are more or less sensitive to this. R2R DACs, for example, such as this one, it's pretty important, but not nearly so important as it is for a Delta Sigma type DAC like mine over there. Delta Sigma type DACs, timing errors can cause lots of distortion. But again, the frequency isn't exactly too critical. It's basically all about that phase jitter, the random timing errors on each individual signal of the clock. If you'd like to know a little bit more about this for the different types of DACs, there's another video on my channel which explains a bit of the difference between R2R and Delta Sigma DACs. And if you're interested in adding Clocklock capability to your DAC, drop me an email. It's not possible with all DACs, but for others, especially with USB input sources, it's an excellent upgrade. Take a look at my website, apexhifi.co.uk, or drop me an email to info@apexhifi.co.uk, and I'll be delighted to talk to you further. Thank you very much for listening.